Hi-oh, rotational inertia. That's the name of the game today. If we look at this picture, we see these tightrope walkers. You ever wonder why they have the long poles? Well, it should give you some insight into today's topic, rotational inertia. Remember, inertia is the resistance to a change in motion. So do these guys want to change their motion? No, of course not. To change, they would end up falling. So the length of these poles probably have something to do with it. Can you imagine them carrying a really short pole? They'd probably spin rather easily. So with rotational inertia, we tend to use the symbol I when we talk about things mathematically. Again, things want to resist their change. If we look at the two pictures here, we have a barbell and a dumbbell. Look where the mass is at. And we'll do this in the lab. If you haven't done it already, when the mass is out towards the edges, it's very difficult to move it. And so it has a lot more inertia. But when it's closer, much easier. Apply this to things that you see out in the world. We have these kids, they're putting their arms out. Why are they doing that? Just like the tightrope walker. It helps preventing them from rotating, from falling off, from pivoting at the point at where they touch the rails of the train track. Earlier this year, we did soup can races. And what you found, I think, was that the broth soups won. And if you think about why that is, chunky soups tended to act like this disc right here. We had chunks of mass out towards the edge. Broth soups did not. So where is the majority of the mass? The majority of the mass is towards the edges. Just like before, when the mass is extended out, just like the barbell versus the dumbbell, like we saw earlier, this was hard to rotate. This one was easy. Well, the ring has the same amount of mass as the disc, only the mass is placed outward. Just like that, it has more inertia. It didn't want to start rolling. It paused for a moment as the other one took off. So let's take a look at a figure skater having the greatest rotational inertia. Think about it. Her arms are stuck out here. She ends up having the greatest rotational inertia. From here we have to extend the idea of this inertia to momentum. If you remember, momentum is mass times velocity. That's regular momentum. Well, inertia depends directly on mass. Since we're talking about angular things, or in other words, things that are rotating, it's the inertia times not the linear velocity, like with regular momentum, but the rotational velocity. And if you remember, rotational velocity is 2 pi r over t. So when we put this together, what we find is that just like regular momentum, angular momentum is conserved as well. What we start out with is what we end up with. If we look at this guy on the left, he has a lot of inertia, hence we have a big I drawn here, but his speed is very, very small. His rotating speed, his omega. However, he pulls his arms in and he speeds up, but his inertia becomes smaller. So it works something like this. As one gets bigger, the other gets smaller. But the amount of momentum that they have stays the same. There's no difference. when it comes to the gymnast or the ice skater or anything. So who has the greatest angular momentum? Neither of them. They both have the same. Who's got the greatest rotational speed? Her. She has the greatest omega. This one has the greatest inertia. A few years back, 2004, you may remember there was a tsunami. And what actually happened was that during the earthquake that caused it, material that was about 600 miles in length and 100 miles wide fell 30 feet closer to the Earth's axis of rotation, meaning the mass got closer. So what do you know? It means the inertia of the Earth became, did you say less? It is less. Well, the speed became greater. But the momentum overall stayed the same. So what happens to the rate of rotation? It sped up. There you have it.